Next talk will be by Ivanov. This is about processes P plus and minus annihilation and frozen antiquity, as I understand.
Yes. I'd like to talk about C plus and minus to proton-to-proton production at the CMD-3. It's an experiment at Novosibirsk. Maybe not many of you knows about it, but anyway. But before we begin, I'd like to give a message shout out to our organizers and you all guys, the participants, that you participated and asked a lot of interesting questions and talks, so thank you. But before I start talking about the experiment, the analysis itself, I'd like to give a rather long overview of the experiment. It's CMD-3 experiment. It's a detector at Web 2000 collider. Web 2000 collider is a unique machine. It is E plus E minus one ring collider with big with really high luminosity, is 10 to 32 at 1 GeV per beam, and the energy range is outstanding. Actually, no other machine covers the same energy range in the non-perturbative UCD region. So that I'd like to highlight the round beam optics that allowed us to obtain such a big luminosity. And also the continuous energy measuring system is based on Compton backscattering that allows us to measure beam energy with precision of like 100 keV or even less. It's a picture of the Web 2000 collider with two experiments, two detectors, SMD and CMD-3. CMD-3 detector is a universal cryogenic magnetic detector. It has a magnetic field of 143 Tesla. It consists of a drift chamber, electromagnetic calorimeter, and top system, its time-of-flight system, and muon counters. Drift chamber is axial with charge partitions. It has a resolution of 100 micrometers in RF plane and about 2 or 3 millimeters along the Z coordinate. Electromagnetic calorimeter consists of several subsystems, but I will not cover it at all. I would just say that it has a radiation length of 13.5 x0. So far, we collected a lot of data at energies below 2 GeV in the center of my system. And actually, earlier this year, we obtained one inverse Winterbarn of integrated luminosity. It was the initial goal of the experiment, so it's a big deal for us. And right now, we are obtaining more information in this region. It's raw omega mesons region. It's important for 2 pion production and 3 pion production that are important for G-2 of muon. In my analysis, I cover this energy region. So here you can see a lot of final states that we are analyzing at CMD-3, and as you can see, a lot of work is already done, but many more is yet to come. So stay tuned and wait for results from our experiment. And here you can see results itself. I'd like to highlight P plus P minus results from P plus P minus. Here you can see form factor of pion. It's very important, extremely important for G-2. As you know, it was a big deal in the community last year, and I think it's still a big deal. And now I'd like to move to topic itself, focus on the proton-antiproton production at the plus minus annihilation. Motivation for this work is pretty simple. There are not a lot of data obtained by now. It was just several experiments. It was Babar and BES3 using ISR technique, and preliminary results from CMD-3, but the main problem was not enough statistics in all of these experiments. And another reason is the fact that threshold region that we're covering in this work is from threshold to GeV in the center of mass system. It contains a lot of information about internal structure of nucleons. It's not important not only in proton antiproton channel, but also in neutron-antineutron channel, but it's separate work, separate analysis. And this internal structure also affects other processes, multi-hadron processes like E plus E minus to 6 charge P pions, or K plus K minus P plus P minus. Also, there are some effects in other channels, but I will not cover them. So far, there are just several phenomenological theories, models that explains this deep in the cross section of these channels. It's connected with the opening of real process for nucleon-antinucleon. So it's important to obtain more information to explain this region, maybe create more precise models to explain. Here you can see the statistics of this work and previous work. As you can see, it's we have 20 times more events, and it's superb to previous results. So it's a big opportunity to analyze this threshold region, not only for cross-section, but also for electromagnetic form factors, but I'll show it later. And before I start talking about selection procedure and other stuff, I'd like to highlight the main goal and main challenge that was imposed in this in our work by the fact that we have a lot of soft momenta antiprotons. Before this energy 1.92 GeV, antiprotons are too soft to pierce through vacuum pipe and to enter the drift chamber main volume. So it stops. The antiprotons stop in vacuum pipe and annihilates, and we don't see the antiprotons itself. We see only secondary particles. But there is another region, so-called collinear events, that the antiprotons are hard enough to pierce through the material and to leave distinctive tracks in DC. So later I'll call this type of events stars, and this type of events collinear events. And what is the main difference between them, that Alonso's workflows for these types of events are completely different. So, yeah. I'll start with collinear events. I'll cover event selection procedure, efficiency, planning efficiency, measuring ratio of electric and magnetic form factors, and track microstation efficiency and visible cross section. Yeah, but to start I shall start with event selection. We select events with two tracks originated from the interaction point that were reconstructed with good quality. They must be collinear, and also the total energy deposition colorimeters must be relatively big to better some like muon, antimuon, mu plus mu minus events or something else, because antiproton will antiprotons annihilate in collimator anyway. So we expect big energy deposition. We expect Drake's moment to correspond to proton-antiproton. This is this cut line, as you can see. And we expect big ionization losses because particles are charged and slow. So we show with this cut, we separate protons and antiprotons from minimum ionization particles like electrons, pions, and stuff. And as I mentioned, we need collinear tracks. It's a cut on a collinearity, like delta phi and delta theta of between two tracks. After selection, we counted all events as signal events. Second step is selection efficiency, but here's the problem, because efficiency for efficiency depends on electromagnetic form factors, because we can parameterize cross-section with two form factors that have completely different angular distributions, and therefore our cuts, imposed cuts, yields different efficiency. Efficiency is, as you can see, there is a 60% difference between efficiencies. So it's important to, beforehand, we need to understand what GE to GM ratio is to obtain the selection efficiency that corresponds to our experimental data sample. For that reason, we fitted angular distributions, experimental angular distributions with angular distributions from Monte Carlo simulations. We obtained distribution for so-called GeV sample. It's a sample with non-zero electric form factor and zero magnetic form factor, and it is this blue dots. And we obtained sample with non-zero GM form factor. It's red dots. It's vice versa. So after we fit it, and we have only we have two free parameters, and one of them is GE to GM ratio. So we obtained GE to GM ratio for all energy points that we have collinear events. You can see it here, and we fitted it with constant function. As you can see, it's there is no internal behavior like energy dependence. Actually, we don't see it on such a small scale. So no new physics in here. And what I forgot to mention that we consider track efficiency, difference in track reconstruction efficiency in Monte Carlo and data, so like this. And we obtain track reconstruction efficiency for both MC sample and data sample using the following procedure. We selected pure sample with antiprotons. It's pretty much the same cuts that we used before, but they are stricter, a bit more stricter. It's a low row of tracks, so it means they are small z of tracks. It means that they are generated from the interaction point. Negative charge is obvious, and ionization losses and momentum response to antiprotons obvious too. And for this sample, for antiprotons, we look for proton pair with the same, pretty much the same CAS criteria. And we are required these tracks to be collinear. And afterwards, we simply divided amount of tracks with pair, proton-antiproton pair, to all events with antiproton. Here you can see comparison of efficiencies for Monte Carlo and experiments. As you can see, there are consistency in almost all cosine theta region. Here you can see ratio of Monte Carlo efficiency in Monte Carlo and in experiment. Okay. Afterwards, after we obtained GE to GM ratio, we can obtain efficiency. Statistical errors in these points arises from the uncertainty in G to GM. So MC data sample size is relatively big. It's almost infinite in terms of the data size, data sample. And here you can see integral efficiency, track efficiency for each energy point. It's important to take into account differences between experiment and Monte Carlo because in some energy points the effect is more than 10%. So it will affect cross-section greatly. And here you can see visible exception for collinear events. It's constant as we expected. Let's move on to stars. Event selection procedure for stars is completely different. We expect to see a lot of tracks in events with relatively small energy deposition because mostly it's pions from the antiproton annihilation. Also, we expect no secondary protons from the vacuum pipe. It means that no particles bumped into protons in vacuum pipe. So it means secondary protons means that it's a background for sure. Also, we require no tracks with small raw coordinates of tracks. It means that they are not originated from the interaction point. It's important because, here you can see distribution. It's important because almost all of the background has small raw of tracks. But some of the signal also has tracks with small raw, but we can't filter this background otherwise. And total energy deposition in calorimeters must be relatively big because antiproton annihilates, so we expect to see at least a couple hundred MeVs. And minimal momentum tracks momenta are bigger than 50 MeVs. It was imposed just to improve resolution and to bring some consistency between Monte Carlo and experiment. After we selected events, we moved to event counting. We see that there is a lot of background. This is distribution of vertex raw coordinates for under threshold points, energy points. We don't expect here to see any signal, but there is some events passed. So, and here you can see distributions for signal region. So we fitted experimental distributions, raw distributions with signal from Monte Carlo simulation and background obtained from under threshold energy points. Here you can see example when we have only one peak at vacuum pipe, and here two peaks, one peak from vacuum pipe and another peak from inner shell of the GeV chamber. The uncertainty of this procedure, systematic uncertainty, is about 2%, and it corresponds to uncertainty in the background model. Here you can see selection efficiency. I'd like to explain this region where selection efficiency drops really sharply. It's connected with the fact that antiprotons in this antiproton momenta are growing here, and some antiprotons starts to pierce vacuum pipe without annihilation, so we simply don't see stopped antiprotons here. So, and afterwards it goes to almost constant value that corresponds to in-flight annihilation of antiprotons. But we don't consider these points at all. There is, after we obtained selection efficiency, we found out a big problem with simulation of antiprotons annihilation. Energy point, here you can see visible cross-section versus energy, and energy points that corresponds to this region have excess cross-section that is connected with the flows of simulation, flows of GeV simulation, GeV package. We don't know exactly what it is. It's maybe wrong d to dx, maybe wrong material densities, maybe wrong model, wrong annihilation cross-section at rest and in flight. Annihilation cross-section, we don't know, but we can effectively correct it with the different pipe thickness in vacuum pipe thickness in the simulation. So we varied pipe thickness in the simulation to take into account this effect. We expect it to be constant, but we don't. So we varied it, and we found out that effective correction is about just 6%, less than 6%. That corresponds to 30 micrometers. After this correction, we see constant cross-section. But here we move to another problem that still annihilation cross-section in GeV is simply wrong, and we can see it by this relation between visible cross-section versus energy in center of mass system. Here you can see stars events, cross-section obtained by stars events. Here collinear events, and there is an unexpected step. And as you can, there is a simple explanation that all antiprotons in this region, almost all antiprotons, they annihilate at rest. But probability to stop in the material in GeV is correct. That's why we have correct energy dependence here. But the probability to annihilate, cross-section annihilation, is in GeV is wrong. The value of annihilation is wrong. That's why the does it work? That's why the value of cross-section is different to doesn't work too. Sorry. And to take into account this effect, we introduced additional parameter in the feet of visual cross-section to obtain this correction, to take into account this step, and also to obtain Born cross-section. We fitted visible cross-section with our Born cross-section model and fighting chloride radiator, and this Gaussian distribution that corresponds to energy distribution in the beam energy distribution. And we also introduced quite modified He square to the feed procedure to take into account these K stars. It's the correction of the cross section. So we fitted it, and here you can see corrected visible cross-section with the fit curve. As you can see, the results are good. So our model describes our cross-section with a good chi-squared. And I think I should move to the results. Here you can see our Born cross-section in a comparison with Bovar results and best results. And what I'd like to highlight that we simply have more statistics, we have better energy resolution rather than all other experiments. But the problem is with stars events because of this effect. So results are only preliminary. It's preliminary results yet for that reason. And also there is a comparison of G to GM ratio in our work and other works. So that's all.
Please, questions? Yes.
I'm a bit confused. It looks like you twice changed the results for jump, yes? To make your model consistent with your data, yes? What is your model?
No. We changed not jump for data, but the data, the parameters of the detector in simulation, because this cross-section was not expected, and we do not think that there is some physics behind it. So it looks like it's simply.
Okay, so in this case you change your Monte Carlo of your detector, yes?
Yeah.
I just wondered, does it change change anything in the analysis of other data? I mean, you not only proton and antiproton you measure with this detector, there are other interesting issues where you consider plus and minus relation, for example, G related to G-2 or.
It's a good question, and the simple answer is no. It does not affect because it's only important for particles that have that are soft, really soft. Momentum of protons here is about 100 MeVs. It's super soft, and in other channels we simply do not see such tracks because we do not have. I will rephrase it. Other channels in our energy region, they are not that good because we can't see threshold of these processes, simply because there are no underlying resonance, or maybe our luminosity is simply not enough to check these regions. But for K plus K minus, it may be important in future because there are some plans to measure threshold cross-section of the K plus K minus and also K short, K long.
Okay, and when you present this thin line, it's kind of theoretical predictions, yes?
No, it's not a theoretical prediction, it's empirical model that we use. It's the same.
Yeah,
the energy dependence is the same as for Born cross-section. It's like slope, and after this slope region, it moves to constant value.
Why is it constant? Why no? I mean, it could be some oscillations or don't know.
Yeah.
Why is it constant?
Yeah, of course, there could be some underlying behaviors, some complex behavior, but we do not see it. Our resolution is not enough to see it. For that reason, we use simply empirical model, but there are several phenomenological models, and I can show some preliminary results. They are not that good yet, because there's this region. But anyway, it's a phenomenological curve from this article that describes threshold energy dependence of cross-section. As you can see, it has the same energy dependence, almost the same. But there are some problems with results of this article, this paper, because there is some tension, and we are working with authors. But I can't explain it in detail right now.
Yeah, but for high energy, there are more data, I mean, and these results should match to the results when you measure this proton antiproton production at high energies. Yes.
Yes, and it's
Or it's also constant.
yes, it matches other results, and also it's in a great consistency with results from higher energies. There are several experiments like BEST-3 that measure cross-section in a higher energy region. So it's consistent, but we do not see any resonance yet here.
One more question.
Okay, thank you for your talk. I have a simple question. So this cross-section at level of 1 nanobar, yeah?
Yes.
Yeah, and what is, how to say, if you compare this total cross-section in plus and minus into hadrons, what contribution or level of total into hadrons?
In this energy region, it's about 2%. So it's quite important, I would say.
Okay, please.
So I have a related question concerning the threshold behavior. So did you already try to feed it with some final state interaction potentials?
Yes, of course. In this paper, authors consider strong interaction in the final states, and we used their data, their curve, to fit our data, our points, and as you can see, it matches greatly, but there are some new results from their newer paper that's quite strange, I would say. So we, in a constant collaboration with them to understand what is the difference.
Okay, let us thank this speaker and the previous speakers, Professor Studenka and Studenikin, all three of them, for excellent presentation, and let us